Okay, so in this video we're going to go over simplifying inverse expressions. All right, now we've already done this in a previous module, but what we're going to do now is we're going to, and we did compositions of inverse expressions, and now we're going to look at some expressions that involve using a trigonometric identity. All right, so for example, our goal was to simplify this following expression. Okay, now right away when I see an expression like this, where you have a cosine, and we have a sum essentially of two angles, right? Now you might see here inverse trig functions, but remember, an inverse trig function, the output of that is some angle in radians or degrees, right? So when I see something like this, I want to think, all right, well, I have an identity to deal with a sum of two angles, right? Cosine alpha, cosine beta, minus sine alpha, sine beta. Okay, so if I look at the two inputs here, the arcsecant 3, arctangent 2, let's take a look at the arcsecant of 3. Right. All right, and again, right, the output here is some angle. I'll call it alpha just so it matches up with our identity here. So arcsecant of 3 is equal to alpha. All right, now, if this is true, just by the way we define inverses, that means that the secant of alpha must be equal to 1/3. Excuse me, getting ahead of myself here. Equal to 3, and then the cosine of alpha through the reciprocal identities is equal to 1/3. All right, and alpha in quadrant 1. All right, since we are dealing with inverses, and the inverse of cosine when it's positive, well, it'll fall in quadrant 1. Okay, so now that means here in quadrant 1, this is alpha. We have this to be 3, 1. Right, so finding y, 3 squared equals to 1 squared plus y squared. Here, so this is 9. Solving for y, we get 8 equals to y squared. Take the square root. And again, here, whenever we're dealing with square roots, plus or minus, but since we're in quadrant 1, we'll stick with positive. Reducing this, since we notice that one of the factors is a perfect square, that becomes 2 root 2. Okay, so now we have found sine of alpha to be equal to 2 root 2 over the value 3. All right. Okay, so we found the two quantities that I'm going to need for my identity here. Okay, so now let's work with the second component here, arctangent of 2. And again, the output is going to be some angle. I'll call this angle beta, just again to keep in line with the with our identity here. So if arctangent 2 is equal to beta, this is true if and only if tangent of beta is equal to 2. Since tangent is positive, we have an angle in the quadrant 1, right, where the angle is somewhere between 0 and pi over 2. Okay, so here beta, let's see, so the y is 2, the x is 1, and you can think of it as a fraction over 1. So finding our hypotenuse here, we get 2 squared plus 1 squared. We get c squared is equal to 5. Take the square root, plus or minus, but since we're dealing with the hypotenuse, we always take that value to be positive. So we get root 5. So now we have sine of beta equals to 2 over root 5. or if you rationalize the denominator, 2 root 5 over 5. Cosine of beta, that would be 1 over root 5. Rationalizing the denominator here, we get root 5 over 5. Okay, and there we go. All right, so now we did all this work. We still haven't gotten to solving our problem here, but now that comes next, right? I have all the components necessary, so the last part really is just kind of putting all of this together. So we have the cosine of the arc secant of 3 plus arc tangent of 2. All right, so substituting in here are variables, or our angles I should say, that we call the arc secant of 3. We have cosine alpha plus cosine beta. We have our identity. All right, and now we just plug in the values, right? Cosine of alpha that we have determined, cosine of alpha is 1/3. Cosine of beta is root 5 over 5. Sine alpha is 2 root 2 over 3. And sine of beta is 2 root 5 over 5. Okay, and we notice here that these have the same denominator, over 15, so I'll just rewrite it as 1 fraction over 15, and this is root 5. Here, we're going to multiply whatever has a root. We can multiply inside the root, so that'll be 5 times 2 is 10. Whatever's outside of the root, we multiply the coefficients, right? 2 times 2, that's 4. All right, and there we go. All right, there is no more simplification that could be done at this point, right? These are not the same roots, so we can't subtract them inside of them, right? So there we go. That is our exact solution to our above expression. All right, let's go over one more example here. This time we'll look at applying another identity. So here, let's say I want to simplify sine of 2 arcsine of negative 4 over 5. Okay. Now, in a previous module, we did problems that didn't have a 2 in there, right? And that would be simply what we would say, that'd be negative 4/5, excuse me. Okay, but now we have that 2, right? And again, this is essentially a double angle, right? Again, always when you see something like this, think of this as an output of being some angle, right? So we have arc sine of negative 4 over 5 is some angle theta, right? Then if this is true, that means if and only if sine of theta is equal to negative 4/5. Now the sign is negative in quadrants 3 and 4, but since we're dealing with an inverse, if we recall, the range of the inverse was negative pi over 2 to pi over 2. So we're dealing with an angle in quadrant 4. All right, so my theta is somewhere right here, right, where the y component is negative 4 and the hypotenuse is 5, which means that our x-coordinate is going to be a positive value. Okay, so let's find that x value. Right, so the hypotenuse squared is 25. The y value squared is negative 4 squared, which is a positive 16. And then the x squared is what I'm finding. So subtract 16 from both sides. We get 9 equals to x squared. And then we take the square root. Right, again, always remember Taking the square root of a square, we'll have a plus or minus. In this case, it's in quadrant 4. The x-coordinate is positive there, so x would be positive 3. Okay. All right, so now if we have sine of theta to be negative 4/5, cosine of theta is going to be 3/5. All right, and how do I know I'm going to need the cosine theta of 3/5? Let's go back to our original problem up here. All right, so we were asked to simplify this expression. All right, substituting here, I call arc sine of negative 4/5 to be theta. We get sine of 2 theta. Right, now again, we need a formula, right? An identity, excuse me, the double angle identity. I don't know sine of 2 theta, right? I simply don't just double whatever the sign is, right? Fortunately, that's not how trig functions work. So this is 2 sine of theta cosine theta. All right, now this is something that I can work with. I know these values, right? 2 sine of theta negative 4/5 and cosine of theta 3/5. All right, and then multiply. We have 3 fractions essentially. 2 can be rewritten as 2/1. So we have 2 times 4 is 8, times 3 is 24. Don't forget to bring that negative along for the right, since there's only one of them. And in the denominator, 1 times 5 is 25. Right, and now we have simplified that expression. So this is how you would use simplifying inverse expressions using identities as well. Thank you.